Okay. Partial differential equations time. So the exam, originally in August, when I set up the calendar, I had the exam for this Wednesday, but I think I'm going to make it next Monday. And it covers two topics, the method of characteristics and the Laplace transform. And in the lectures after that, there are 3 or 4 lectures, plus the lecture on Wednesday. We're going to begin to talk about orthogonal expansions in Fourier series. So in the book by Logan, for example, this is chapter 3 and a little bit of chapter 4. Okay. Any questions about problems you would like me to do or redo?
In the Farlow book, can you go over the last question? I think it was 6 for lesson 5.
Lesson 5, problem 4.
Well, give me 1 second. I think it was 6. Yeah, lesson 6. I mean, question 6, sorry.
Okay, so lesson 6, problem.
No, lesson 5, problem 6, sorry.
Okay, so lesson 5, problem 6 refers to problem 4. Problem 4 refers to problem 3. So let me do all 3 of those, 3, 4, and 6. Okay, so this is Farlow. Lesson 5. Start off with number 3. Number 3 is to find the first few terms of the Fourier series for the function f of x equals 1. Wow, okay, so f of x equal 1. So that has a very simple graph. The graph of the function is that. So this is y equals f of x equals 1. And we want to find the Fourier series. So we want to find the Fourier sine series. So just an expansion in size. So we want to be able to write f of x as a sum from 0 to infinity, some Fourier coefficient a sub n times the sine of n pi x. And equals 1. So if we multiply by sine mx, this is the sum, n goes from 0 to infinity, an sine n pi x sine m pi x. And if we integrate from 0 to 1 with respect to x, we can interchange summation and integration. That's a real theorem in advanced calculus or analysis, but And what do we get? So if you integrate the sine, you get -1/m cosine of mx evaluated from x equals 0 to x equal 1. And so this is -1/m. Oops, sorry, I left out the pi. M pi x. Yeah. So this is 1/m pi. So this is cosine of m pi minus cosine of 0. And this is -1/m. This is -1 to the m minus 1. So if m is even, this is 0. If m is odd, this is -2. So we get 0 if m is even, and 2/m if m is odd. Oops, I keep leaving out the pi. Pi, pi, pi. Okay. Any questions about this so far? So we want to find the first 3 or 4 terms of the sine series for phi of x, so equal to, for f of x equal 1. Let me just make sure I use the same notation that the book is using, which is phi of x. So if I take phi of x, which is 1, integrate by sine m pi x, I get -1/m pi cosine m pi x from 0 to 1. When m, so cosine of m pi x is -1 to the m. -1 to the m minus 1 is 0 if m is even. It's 2/m pi if m is odd. What is this integral? So we have the orthogonality. So we have the orthogonality relations for the sine. Let me just. So we want to know what is the integral from 0 to 1 of sine of n pi x, sine of m pi x dx. And I already worked this out. This is sort of a standard calculus problem. It's 0 if m is not equal to n, and it's equal to 1/2 if m equals n. So what we get is the following. For the function phi of x equal 1, for x between 0 and 1, if we were to write phi of x as a sine Fourier series, n equals 0 to infinity, an sine n pi x. Of course, when n is 0, sine of 0 is 0, so we can start this with 1. We get the following formula for a sub n. We take phi of x sine mx, integrated from 0 to pi, from 0 to 1. This is summation and goes from 1 to infinity, an integral from 0 to 1 sine m pi x sine n pi x dx. This is summation and goes from 1 to infinity. Well, but this is 0 except when m is equal to n. So what we have on this side is a sub m times a half. And what we have on this side is, so let me just reverse it. So a half a sub m is equal to 0 if m is even, and it's equal to 2 over m pi if m is odd. So a sub m is equal to 0 if m is even, 4 over m pi if m is odd. All right. So these are our Fourier coefficients, and our Fourier expansion is 1 is equal to, we're only summing over the odd values of n, so I can change m to an n, that's just changing the letter, no big deal. So this is 4 over pi sine pi x plus 4 over 3 pi sine 3 pi x plus 4 over 5 pi sine 5 pi x, and so forth. So these are the first 3 non-zero terms of the sine series for the function 1. Let me just actually graph this just to see what it looks like. So let me share the screen with Maple. Oops. I don't want to do that. I don't want to do that. What I want to do is open some version of Maple. Here we are. Okay, so we have the function, I'll just call it f. This is 4 over pi times the sine of pi x. Let me call this f1. And if I plot f1 from 0 to 1, oops, f1 of x. That's what it looks like. There, that's drawn to scale. Okay. Now, suppose I take the next sine function, f3, which was 4 over 3 times pi times the sine of 3 times pi x. And let me graph the sum of these two, f1 plus f3 of x. And actually, while I'm doing that, I should plot the constant function 1 in here, because that's what we're comparing it to. Yeah. So the red line is the constant function 1, and this is the sum of the first 2 terms of the Fourier series. Let's look at the next term. 5, 5, 5. And suppose I add in here also f5 of x. So the first 3 terms give us a graph that looks like that. So let's try and make this more interesting for, let's say, n from 1 to capital N do. And suppose I want to define the function f 2n minus 1. So this is going to be 2n minus 1, 2 and plot sum f 2 times n minus 1 of x, x going from let's see, does this make sense? So this is the sum of the first capital N of these functions. And I want to plot this from 0 to 1. So let's just check. Suppose I let n be equal to 3. So, I know what I want to do. Okay. So so why isn't this? Well, let's see. I don't want to spend too much time on this. I'm just going to write down the next couple of functions physically, as they say. I'll make this 7. Make this 9. Make this 11. $13. And let me just renumber these actually. I'm just going to call this the second one, third, fourth, fifth, 6, 7, 8. Let's see. Perfect. Okay. So this is the sum of the first 3 functions. That's the sum of the first 4. And the idea is just to see how much better this approximates the constant 1. That's the sum of the first 5. That's the sum of the first 6. That's the sum of the first 7. That's the sum of the first 8. So it's just kind of interesting to see how this goes. Okay. All right. Anyway, So that's the Fourier series. That's problem number 3. What about problem number 4? Problem number 4 is to solve the initial boundary value problem. The initial boundary value problem, where the PDE is the diffusion equation, U sub t equals uxx for x between 0 and 1. The boundary conditions at the ends of this, whatever we think of it is, a y or whatever, at the left end, u at x equals 0, u of 0 t is always 0, and at the right end, where x is 1, u of t is always 1 for all t from 0 to infinity. And the initial condition is that we have a uniform temperature distribution, u of x 0 is equal to 1 for x between 0 and 1. So we were trying to solve this problem by separation of variables. So we suppose that our function u of xt can be written as a product of a function of x and a function of t. And when we differentiate this with respect to t, what do we get? So the partial with respect to t of u of xt is the partial with respect to t of x of x, t of t. This is x at x, t prime of t. And the second partial of u with respect to x, that's the second partial with respect to x of x of x, t of t. That's the second derivative with respect to x of the function capital X, t of t. So when we equate these two, so ut equal uxx implies x of x, t prime of t is x double prime of x, t of t. So we get x double prime of x over x of x is equal to t prime of t over t of t. This function of x equals this function of t. That can only happen if this is a constant. So we're led to two ordinary differential equations, one for x and one for t. We get that t prime of t, this is the derivative with respect to t, is equal to k t of t. Oops, I left out alpha squared. Was that, well, in this case, alpha is 1. So t of t is some constant times e to the kt. And K we expect to be negative because we expect this function to be going to 0, so we can write K as minus alpha squared. So we get the temperature as a function of time is some constant A, lambda is the notion, e to the minus lambda squared T. And x double prime of x is K, x of x, which is minus lambda squared x of x. Which means, so for this second order ordinary differential equation, if this is negative, we expect this to be a linear combination of sines and cosines. So for some numbers A and B, this will be A lambda A times the cosine and the sine, A times the sine of lambda x plus B times the cosine of lambda x. So u of xt will be x of xt of t. This is some linear combination. This is some function of e to the minus lambda squared t, a sine lambda x plus b cosine lambda x. And if we look at the boundary conditions, u of 0t is equal to e to the minus lambda squared t. When x is 0, sine is 0. When x is 0, this is b. This is b e to the minus lambda squared t. But the boundary condition is that this is equal to 0, which means b has to be 0. So u of xt is just a sine function. It's some constant a times e to the minus lambda squared t sine of lambda t. And if we look at the initial condition, u of x comma 0 is a. When t is 0, this is 1. Oops. Let's see. Here I said x equals 0. Here I want to get oops, what did I do? Sine lambda x. Thank you. Thank me. So u of x comma 0 is a sine of lambda x. And my initial condition, u of x 0, is equal to I want to look at the other boundary condition. Because our two boundary conditions were at the ends, u of 0t was 0 and u of 1t was 0. So if I compute u of 1 comma t, this is equal to a e to the minus lambda squared t sine lambda is 0, which only happens if sine lambda is 0, which only happens if lambda is a multiple of pi. So for ut equal uxx with the boundary conditions u of 0t equal u of 1t equals 0, we get the solution u of xt is a function of the form, I'll write it as a sub n e to the minus lambda squared t. Lambda is plus or minus n pi, n squared pi squared t times the sine of n pi t. Right. So any solution of this form satisfies the differential equation and it satisfies the boundary condition, and any linear combination of these things does. If I take this and I sum this over any finite range of values of n, this also gives me a solution of the differential equation. But I also have let's see, I also have the initial condition. The initial condition is that u of x0 equals 1. So if I plug that into this, u of x comma 0 is sum over n, a sub n sine of n pi t equals 1. So these coefficients a sub n are exactly the coefficients of the Fourier series. So a sub n is equal to 0 if n is even, 4 over n pi if n is odd. So u of xt is, let me just write down the first few terms. So when n is 1, I get, so this is e, I get, sorry. When n is 1, I get 4 over pi e to the minus pi squared t sine pi t. When n is 3, I get 4 over 3 pi e to the minus 9 pi squared t. This should be an x here. X sine 3 pi x. When n is 5, I get 4 over 5 pi e to the minus 25 pi squared t sine 5 pi x, and so on. Okay. So this is the solution of problem 4. Any questions about this? Oh, if you came in a little bit late, this is where we are. So exam 2 is a week from today. It's covering mostly the method of characteristics and the Laplace transform. And then subsequently, what we're going to be covering is a little bit what I've been talking about just now, orthogonal expansions and Fourier series in the solutions of partial differential equations. Okay. Now, problem number 6 says keep the same diffusion equation. So the PDE is the equation U sub t equal UXX, x between 0 and 1. The same boundary conditions that at the ends of this rod, the temperature, if that's what we're measuring, is kept at 0 for all time. But we want to change the initial condition. Instead of the initial condition being U of x0 equals 1, the initial condition is U of x0 equals x minus x squared. Okay. So now for our rod, at t equals 0, this is the distribution of the temperature. Right? It's this parabola. 0 at the ends, and it's going up like this. So let's just go back and see what we had found already. So from the PDE and the boundary conditions, we get that U of xt is some Fourier series or some function of the form a sub n e to the minus n squared pi squared or n pi squared quantity t times the sine of n pi x. So if we look at the initial condition at t equals 0, U of x comma 0 is summation n goes from 1 to infinity, a sub n, this is 0, sine of n pi x is equal to what? It's equal to x minus x squared. So we must find the sine Fourier series for x minus x squared. Right? So the procedure is always the same. Suppose x minus x squared is this sum, summation n goes from 1 to infinity, a sub n sine n pi x. Multiplied by m, by sine of m pi x. So x minus x squared times the sine of m pi x is going to be summation n goes from 1 to infinity, a n sine of m pi x sine of n pi x. Integrate from 0 to 1, we get the integral from 0 to 1 of x minus x squared sine of m pi x dx is the sum from 1 to infinity, a sub n, integral from 0 to 1 sine of m pi x sine n pi x dx. Okay. I'm just taking this equation, integrating term by term from 0 to 1. And we've already calculated this. This is equal to 0 if m is different from n. And if m is equal to n, we get, depending on whether m is even or odd, let's see, let me find where I had written down that result. This is equal to, oops, here it is. This is equal to 0. This is equal to a half if m equals n. So this equals a half a sub m. Of course, we have to know how to do this integral. So we can do this integral by integration by parts. Let's try and do it. So we need to compute the integral from 0 to 1, x minus x squared sine m pi x dx. Let's see, integrate by parts. Well, it's going to take 2 steps, so let's just do it. So suppose we have x minus x squared and sine m pi x. The derivative of this is 1 minus 2x, and the integral of this is minus 1 over m pi cosine of m pi x. So let's just call this I, this integral, I sub m. I sub m is equal to x minus x squared times minus 1 over m pi cosine m pi x evaluated from 0 to 1, which is 0, minus the integral like this. So that's minus the integral of 1 minus 2x minus this makes this plus 1 over m pi cosine of m pi x dx from 0 to 1. And then I need to integrate this. And then again, I'll do integration by parts. If I have 1 minus 2x and cosine m pi x, this is minus 2, and this is 1 over m pi sine of m pi x. So the integral from 0 to 1 of 1 minus 2x cosine of m pi x dx is this times this, 1 minus 2x, 1 over m pi sine of m pi x from 0 to 1. But at x equals 0 and x equal 1, this is just going to be 0, minus this integral. So it's minus, this times this is minus, makes this plus 2 over m pi, integral from 0 to 1, sine of m pi x dx. That's equal to 2 over m pi minus cosine m pi x over m pi from 0 to 1. when x is 1, this is, let me take the minus sign outside. So when x is 0, you get 1 over m pi. And when x is 1, you get plus or minus 1. So this is minus 2 over m pi squared. And if m is odd, you get minus 1, you get minus 2, makes this plus 4 if m is odd, and it's 0 if m is even. So let me write down what we have. We have the integral from 0 to 1 of 1 minus 2x cosine m pi x dx is equal to 0 if m is even, and 4 over m pi squared if m is odd. So the integral that I need to find, I sub m, is equal to 1 over m pi times this integral, zero if m is even, 4 over m pi squared if m is odd. So that's equal to 0 if m is even, and 4 over m pi cubed if m is odd. And all of this is equal to 1/2 a sub m. So my Fourier coefficient looks like it's equal to 8 over m pi cubed if m is odd, and 0 if m is even. So there's at least a 50-50 chance this is right, but there's a big calculation. I could have made a mistake, but looks so good so far. So this says that the sine, the Fourier sine expansion is x minus x squared equals, when m is odd, I have 8 over pi cubed sine pi x plus 8 over 3 pi cubed sine 3 pi x plus 8 over 5 pi cubed sine 5 pi x, and so on. So what this gives us is, if we start with the PDE, this is page 10. So, sorry, this is page 9. So this is page 10. When we started with the PDE, ut equals uxx, the boundary condition u of 0t equal u of 1t equals 0, and the new initial condition u at x at time 0 is x minus x squared, we get a solution which is an infinite series of the form u of xt equals e to the minus n pi squared t sine n pi t times these coefficients. So, but we only have the odd values. I can factor out 8 over pi cubed e to the minus pi squared t sine of pi x plus e to the minus the quantity 3 pi squared t sine of 3 pi x over 3 cubed plus e to the minus 5 pi squared t sine 5 pi x over 5 cubed, and so on. Phew. So, for whoever asked how to solve in Farlow problem 6 in lesson 5, only took an hour, but that's the solution. It's very nice. I mean, we're going to spend more time on after Thanksgiving in the last 4 classes or so studying these Fourier series, and which is an example of what is called an orthogonal expansion, but that's what it is. Okay. Any questions about solving a problem using either the Laplace transform or the method of?
Yes, can you go over the dimensional characteristics?
I'm sorry, go over what?
Yeah.
The
Can you
method of
explain?
characteristics?
Yeah.
Okay. All right. I'll do some problems. So this is method of characteristics for first order Cauchy problems, which means we have an initial condition only. So the basic example is we have a partial differential equation where partial of u with respect to t plus maybe some function a of xt times the partial of u with respect to x of xt. Let's look at the homogeneous case equals 0. So this is for x from minus infinity to infinity and t greater than 0. And we have some initial condition that u of x comma 0 is some function phi of x. And the general method is as follows. Solve the ordinary differential equation, dx dt equals a of x of t comma t. And with the initial condition that x of 0 is something, we'll call it x0. And then we make the following important observation. So for this function that solves this ordinary differential equation, if I look at u evaluated at x of t comma t, so this is some curve. Right? X is a function of t. So along this curve, whatever it looks like, evaluate u at x of t comma t. And if let's differentiate this function of t with respect to t. So we use the chain rule for a real valued function of two variables. This is the partial of u with respect to t dx dt plus the partial of u with respect to x. Sorry, partial of u with respect to x, the first variable, dx dt, plus the partial of u with respect to t dt dt. This is just one. So this is the partial of u with respect to x. What is dx dt? Dx dt is a of x of t comma t, u sub x at x of t comma t, plus u sub t at x of t comma t. But this is just my differential equation. This is equal to 0. Right?
Teaching Mrs. Tingle, the family way in the private life of Sherlock Holmes.
Okay. Equals 0. So u of x of t comma t is constant, because the derivative is 0, is constant on the curve tx of t, or x of t comma t. This curve is what is called a characteristic. And u of x of 0 comma 0, which is u of x naught comma 0, this is just the initial condition. This is phi of x naught. So u of x of t comma t, if this is constant on the curve, that's the same as u of x of 0 comma 0, which is phi of x naught. Let's invent an example. Suppose I have the equation u sub t plus 5 u sub x equals 0. And the initial, so this is my PDE. And my initial condition, let's say, is u of x comma 0 equals x squared. So let's try to solve this equation. So my function a of xt is equal to 5. So I want to solve dx dt is equal to 5. So x of t is 5t plus a constant. That constant is x0. So x of t is 5t plus x0. So u of x of t comma t is, so my function phi of x is x squared. So this is phi of x0, which is x0 squared. What is x0? X0 is x minus 5t squared. So I get this u of xt is equal to x minus 5t squared. Okay. All right, so let me just review. So here's this first order differential equation, ut plus 5ux is 0. And my initial condition is that at time t equals 0, u of x0 is x squared. So this function a of xt is equal to 5. So dx dt is 5. What function has a derivative equal to 5? 5t plus a constant. The constant is just the value at 0, x0. So x of t is 5t plus x naught. So u of xt comma t is just phi of x naught. That's x naught squared. X naught is x minus 5t squared. Okay? So if this is correct, well, let's check. Check. Suppose u is x minus 5t squared. If I differentiate with respect to t, I get 2x minus 5t times minus 5 is minus 10x minus 5t. If I differentiate with respect to x, I get 2 times x minus 5t. If I multiply by 5, I get 10. I add these two, ut plus 5ux is 0. When I let x equal 0, when I let t equal 0, u of x comma 0 is x squared. So this is my PDE, and this is my initial condition. So it all checks. All right. So there's a lot of noise outside at the moment for some reason. So I hope you can hear, but that's an example. Right.
And then the Laplace transform for PDEs, can you do one?
I'm sorry, can you speak up, please?
Yes, for the Laplace transform, can you go
All right, so you want me to, so I should do an example using the Laplace transform?
Right. Because for all PE, we learn, right? Wow, what about for PDE using the Laplace? Thank you.
Right. Okay. I mean, there are people working outside making a lot of noise, so it's hard to hear. But so you're asking for a problem using the Laplace transform. Any particular problem, or should I just pick one? Right. Yeah. Okay, so let me do an important second order equation. Suppose I look at the following PDE. Partial view with respect to t is the second partial view with respect to x. Let's say for x between 0 and 2 and t greater than 0. And let's say we have the initial condition that u of x0 is equal to 3 times the sine of 2 pi x, and the boundary conditions are u of 0t and u of 2t are equal to 0. So we have something from 0 to 2, and at the end, 0 and x equals 0 and x equal 2, let's say this is temperature. Temperature is fixed and constantly equal to 0, and when we start, the temperature at x is given by this function. So kind of looks like this. So this sine wave is the initial condition. And so for this differential equation, let's take Laplace transform. So we have L of u sub t equals L of u xx. So suppose we let u of xs be the Laplace transform of u of xt, which is the integral from 0 to infinity, u of xt e to the minus st dt. So if we differentiate twice, this is the Laplace transform differentiated twice. And if we differentiate with respect to t once, we get su minus u of x0. That's su minus 3 times the sine of 2 pi x. So this equation says that, let me just say it's like this minus this. So the second derivative of u minus su of xs equals minus 3 sine of 2 pi x. So this is a second order linear differential equation that we have to solve. So I'm not going to do it because it'll just take me a long time right now. But so we solve for u of xs and then use the inverse Laplace transform. It's just too noisy right now for me to be able to do this stuff, but I will, maybe I'll do this on Wednesday first thing just to work out the details. But the important step is to use the Laplace transform to reduce your partial differential equation to an ordinary differential equation. And we know how to solve linear second order PDEs. U is a function of x. So this capital U is just going to involve sines and cosines of square root of s, right? So, I mean, we know we're going to get that for the homogeneous equation, u of sx is going to be some constant e to the square root sx plus another constant e to the minus square root of sx. That's for the homogeneous. And then we use the method of variation of parameters or whatever other technique you like to solve this non-homogeneous equation.
Professor, only in the Cauchy problems we need to apply the knowledge how to separate the PDEs, or I can use another method previously used when the separation.
So if there's a problem that just says solve the PDE, you can use any method you wish. If the problem is says use Laplace transform or use the method of characteristics, then that's what you have to do. But if it just says solve the problem, anything you do that solves the problem is perfectly okay.
Okay, thanks.
Let me do one more problem with Laplace transform, and that'll be good. Let's see. Let's try something like this. Suppose I have let's see. I'll just suppose I have u sub t plus 3u sub x equals x squared. And I have some initial condition. So this is going to be for x greater than 0 and t greater than 0. And I have, let's say, I'll make it a very simple initial condition, namely that u of 0t and u of x comma 0 are always equal to 0. So what do I have? I have the Laplace transform of ut plus 3ux. That's the Laplace transform of u sub t plus 3 times the Laplace transform of u sub x is the Laplace transform of x squared, but this is with the Laplace transform is with respect to t, so this is the same as x squared times the Laplace transform of 1. The Laplace transform of u sub t is s u of x comma s minus u of x comma 0, which is 0, plus 3 u sub x of xs equals, what's the Laplace transform of 1? It's 1 over s. So this is an ODE that I need to solve. Let me divide by 3. This says that u sub x du dx plus s over 3 u is equal to x squared over 3s. Okay. S is a parameter, s is a constant. How do we solve this differential equation? Right? If we multiply by e to the s over 3x, we get e to the s over 3x u prime plus s over 3 e to the s over 3x u equals x squared e to the s over 3 over 3s. This is e to the s over 3x u prime equal to this. So that means e to the s over 3x times u of xs is the integral x squared e to the s over 3 over 3s dx, which is, x is a constant. So this is e to the s over 3 over 3s. The integral of x squared is a third x cubed, makes this 9x cubed plus a constant. So we get u of xx is equal to x cubed over 9s plus c e to the minus s over 3x. Right? So and then you use the Laplace transform table to find the inverse Laplace transform of this. Okay. Let's just double check that this is correct. So what this is saying is, for the ordinary differential equation, dy dx equals plus s over 3y equals x squared over 3s. Suppose we let y equal x squared over 9s plus c e to the minus s over 3x. So in this case, dy dx is, sorry, this is a 3. 3x squared makes x squared over 3s minus c s over 3 e to the minus s over 3x. So dy dx plus s over 3y is x squared over 3s minus cs over 3 e to the minus s over 3x plus s over 3 times y. So that's, oops, something's not good. So x cubed over 9s. So dy dx is x squared over 3s minus s over 3x plus s over 3 times y. So yeah, let me just double check this. So if this differential equation is okay, then you multiply by e to the s over 3x. This is e to the s over 3x u differentiated equals this. So e to the s over 3 times u is this integral with respect to x. That's x cubed over 9s e to the s over 3 plus a constant. So I get x cubed over 9s plus c e to the minus s over 3x. And x squared over 3s. So something here isn't working out right. So have any of you solved this little differential equation yet? Assuming this is my differential equation, if I just write u as y, so it looks like an ordinary differential equation. dy dx plus s over 3y is x squared over 3s. So when I multiplied by e to the s over 3x, then this thing differentiated is this equals this. So that's x cubed. Let's see. Let me just take a fresh piece of paper to solve this differential equation. If I have dy dx plus s over 3y equals x squared over 3s, I multiply by e to the s over 3x. Over 3s. And of course, this is just e to the s over 3x y differentiated. So this is the integral of x squared e to the s over 3x over 3s e to the s over, sorry. Yeah, that's my mistake. X squared e to the s over 3x. So this is 1 over 3s, the integral of x squared e to the sx over 3 dx. And then you have to integrate this by parts. twice. To find the solution. Okay, well, think of that as a nice homework problem for Wednesday, if you like. Just takes some work, right? So you expect the 400 level math class to have some interesting problems, which means they might take a lot of time to solve, but that's what we have here. Okay.
Professor, the last question. How many questions would be on the next exam? 3, 4?
Yeah, 4 or 5. You can ask me on Wednesday. I'll know better then. Right. The exam is next Monday. It's not on Wednesday.
Okay.
Okay. All right. That is it for today then. See you in some sense Wednesday morning.
Thank you. Take care.
Okay. Bye all.
Thank you.